now that I have this case, right? So now I would like to look at, okay, the objectives of, the reason why I've kind of given you a brief background of, inducing aggregation is because I would like to look at settling of aggregates. Okay, so far we were looking at, a simple case of, I have a spherical particle settling in a fluid, okay, a stagnant fluid. Now I would like to look at settling of aggregates. So now if you ask me a question as to know how these aggregates form, okay, whatever background that I've given so far would help, right? Okay, so you start with a dispersion, stable dispersion, add additives, and you basically end up with this configuration, right? I would like to think about settling of aggregates. So what kind of formulation do you think I should use? Okay, do you think whatever we developed for the case of single particle settling, do you think it's going to work? Do you think that whatever settling principle that we kind of formulated for the case of single particles, do you think that's going to work with aggregates? So it turns out that it's not going to work. Okay, but the reason why the settling of aggregates is much more complex. Okay, number one is that you may have aggregates of different sizes in the right. I have this nice dispersion and I go from this state to this state, right? I form aggregates, but aggregates could be of different sizes. Okay, and because these are particle clusters, okay, these aggregates can also deform, right? They may change their size, they may change their shape. Okay, it depends on whether these aggregates are kind of settling in a quiescent liquid, okay, that's a stagnant liquid, or is it in a flowing flowing condition. So everything becomes important. Okay, so we're going to look at a simple and so when it comes to the type of aggregates that are typically formed, people use a concept called, there's a concept called fractal aggregates. Okay, so what you're looking at is 3 pictures, okay, of typical aggregates that people kind of have looked at in the literature, and there are some ways of characterizing these aggregates. Okay, and this is basically done by using a concept called fractal dimension. Okay, so the reason why this fractal concept kind of is applicable here is because in a lot of cases the aggregates that form, they're kind of self-similar. Okay, what I mean by that is, if I look at a case B here, I look at aggregates in this small box, okay, or I go on increasing the box size, right? It turns out if I kind of do an analysis of the structure of the aggregates in terms of the number of particles in that box, in terms of the way the particles are arranged, it will more or less look very similar. Okay, okay, so therefore the fractal kind of concepts are typically used in characterizing aggregates. What you're looking at is a case where there are three aggregates which are of very different morphology, right? In one case it looks more like a linear, right, aggregate. In the second case it looks like more like an open network of particles, okay, and in this case is a more compact network, right? What people do is, we know that if you take, say, mass of the particle goes as volume of the particle into density, right? Now what I can do is, I can say mass of the particle, which is a function of radius, basically goes as 4/3 pi r cube into rho p, right? Right? Think about a solid particle, right? Think about a solid particle, and if I were to start from the center, if I go radially outward, I can say that the mass of the particle basically goes as radius to the power of 3, right? Now that is the case if I have a particle which is completely or an aggregate which is completely filled with particles, right? Or that is actually valid for a solid particle, right? There is no spaces, right? Now I go to a case where I have, okay, maybe I have a picture, okay, here, right, that your mass of the particle going as r power 3 is only valid for a completely solid aggregate, right? Now the fact that I have a lot of vacant space here, okay, there's a fluid that is also in the aggregate, right? Therefore your MP will go as r power some dimension df, okay, where this df is less than 3, right? And this df is what is called as a fractal dimension, okay? And typical values of df is that if you go for an aggregate in a 3 dimension, the value can go anywhere from 1 to 3 is a maximum, okay? And if you're working with 2 dimension, it can go from 1 to about 2, because the maximum that you can have is power is 2, right? If you look at the picture here, in A, what you see is an aggregate of fractal dimension 1.21, okay? In B you have a fractal aggregate which is a fractal dimension 1.75, okay? In the case C you have an aggregate which has a fractal dimension of 2.05, okay? And what kind of aggregates form and whether the fractal dimension is 1.75 or 2.05, it depends on, again, the kind of aggregation that happens in the system, okay? A is a case where what was done is you have a container, you have, say, a positively charged particle. Now what you do is you add a negatively charged particle to it, okay? When that happens, what will happen is the moment there is a contact between a positive and negative particle, there is a cluster formation, maybe a 2 particle cluster. Now when the next one comes, it can either, I mean, of course, it can go at other location, but it can either go here or here, right? In that sense, there is a formation of a linear aggregate, and that is what leads to a very low fractal dimension of 1.25, okay? And what you see in the case B is what is called as a diffusion limited aggregation, okay? What does this mean is that again you have a dispersion of particles. The moment a particle comes into contact with another particle, they just aggregate, okay? So in case of diffusion limited aggregation, people talk about what is called as a sticking probability, okay? And sticking probability is very, very high in the case of diffusion limited aggregation, because the moment there is an encounter between a particle and another particle, or a particle in the cluster, the particle comes and attaches, that is it, okay? However, in the case of case C, which is what is called as a reaction limited aggregation, what will happen is a particle joins an aggregate, okay? It can also it will continue to rotate until it basically finds a more stable configuration, and that leads to the formation of more kind of a compact structure, okay? The reason why I am trying to say all of this is because understanding settling of aggregates is very complicated, because you should know about the kind of clusters that form, okay? Whether the clusters are linear like this, okay? Whether they are more open structures like here, or whether it's a more compact structure, okay? So therefore you would have to worry about the morphology of the aggregates when you are trying to deal with settling of aggregates, okay? Okay, so in the remaining class, I'm just going to, again, I'm going to use a lot of assumptions, okay? Let's say that we have an aggregate, okay, something like that, okay, the particles are all connected, okay? I would like to look at the settling of this, okay? I'm going to assume that these aggregates are impermeable, okay? What I mean by that is there is no exchange of the solvent, okay, between the aggregate and the surrounding, okay? Because we know that these aggregates are, it's a composite. You can think about aggregate as a composite particle, right? There are particles, of course there is a fluid, right? But now if I assume that there is no fluid exchange between the aggregate and the surrounding, okay, they are what are called as impermeable aggregates. And let us say that I have a simple case of a dispersion which contains say 15 nanometer particles, okay, and say that I have made the particles to aggregate and I have formed an aggregate which is like say some dimension, some example of say 500 nanometer particles. There is an aggregate of 500 nanometer dimension which I am able to form starting with a 15 dispersion that contains 15 nanometer particles, and I have done that by adding additives, okay, it could be salt or polymer or whatever, okay. Now it turns out that even if I assume, okay, even if I assume that this is a really densely packed aggregate, okay, say that what could be the maximum packing density, if I assume that I have formed an aggregate, okay, and this is an aggregate of particle, and say that this is the most dense spherical aggregate that you can think of, okay. What do you think would be the packing fraction of particle in the aggregate? Because I said that these aggregates are, you have particles, of course there is a space where there is fluid as well, right? And I said that it's impermeable, okay, therefore there is a particle plus there is also a fluid, right? What could be the maximum fluid contained? It depends on the kind of packing that I am going to assume, right? If I say that the particles in the aggregate are randomly packed, okay, your packing fraction is going to be 0.64, right? That is the maximum packing density. If I say that somehow I have a way of making an aggregate where all the particles are kind of orderly arranged, some kind of HCP kind of arrangement, hexagonal closed packing, is going to be 0.74, right? Even if you take the most dense aggregate, it turns out that the typical number of particles that you may have is of the order of 27,000 particles, okay. So what I have done is I have taken a dispersion of 15 nanometer particles, okay, and then I have made a aggregate by adding salt or polymer, and if I assume that the density of the size of the aggregate that I have formed is 500 nanometer, if I assume some packing density, I can roughly calculate what is the number of particles in the aggregate, right, by a simple geometric argument. And it turns out if I use a packing fraction of 0.74, this aggregate will consist something about 27,000 particles, right. Now we know that any dimension, okay, which is sub micrometer size range, we know that if I were to calculate the Reynolds number, right, your NREP, okay, is going to be definitely less than 1. Therefore, I can still assume the aggregate to be settling in the Stokes regime, right. So, right, I can assume that, right, because I have made a 500 nanometer particle, say that I have a way of somehow getting what is the rho of the aggregate, okay. I have an aggregate of like say size D aggregate, and that is settling under the action of gravity, and say that I have some way of getting what is a rho aggregate. I can actually, if the fact that your Reynolds numbers are less than 1, whatever formulation that we have done for the settling of aggregates, which is okay, ut is g dp square into rho p minus rho divided by 18 mu, I can actually use exactly the same formulation. I can write this for settling velocity of aggregate, which is g into d, now aggregate dimension square into rho of aggregate minus rho divided by 18 mu. I am of course talking about isolated aggregates, okay, right, settling in a fluid, right. Is that okay? Any questions? Right? All that is being done is, I'm just saying that, the aggregates that are formed, of course they contain a large number of particles because of the fact that the dimensions are, still sub, micrometer. Okay, I can still, use the Stokes formulation, because your now Reynolds number of the particle, okay, or the aggregate if you want to call it as, would still be less than 1. I can actually use the same formalism that I use for settling velocity of the particle. No, you can calculate that, right? Because I said that, if the particle dimension, again, you would have to look at the particle dimension. It turns out, if it's a 500 nanometer particle, okay, right, and if I have this settling in water, if I were to take the density of water and this, right, it turns out, if you calculate Reynolds number, it will definitely be less than 1. Okay, yeah. Okay, so now when you're working with aggregates, it turns out that, the properties of the aggregates are in between that of the, so properties are in between the properties of particle and the fluid. Okay, what I mean by that is, your rho aggregate, right, which is the density of the aggregate, I can write this as rho of particle, okay, times 1 minus epsilon, I'm going to define what is epsilon in a while, plus rho of the fluid times epsilon, where epsilon is what is called as a fraction of liquid in the aggregate. Okay, that's a fraction of liquid in the aggregate. That gives you the liquid fraction, and 1 minus epsilon will give you the solid fraction. Okay, so therefore, you can say that, the density of the aggregate is rho of particle times the particle fraction, okay, plus rho of fluid times, fluid fraction, right? Okay, therefore, if you think about density of the aggregate would always be intermediate to the density of the particle that formed the aggregate and the fluid in which, it is dispersed, right? So therefore, I can actually substitute for this. Okay, I can substitute for this in the expression for, the UT aggregate. I can simplify this further. Can you do that? UT aggregate is GD aggregate square into, instead of rho of aggregates, I can just write it as rho of particle into 1 minus epsilon plus rho of fluid, okay, into epsilon, okay, minus rho of fluid, right, and divided by into right. If you just simplify this further, that's what you would get, right? Yeah. Now, okay, so what I can also do is, I can define the, so I can say that the volume of the aggregate, okay, the volume of the aggregate is equal to the number of particles that I have in the aggregate, okay, or basically I do, okay, let's put it this way, okay. Now I want to, so okay, let's say that, I have Of course, I don't have a way of calculating epsilon, right, which is the, but of course, if I can do some assumptions, right, I can say that, the maximum value of this is going to be 0.74, okay, if I assume a ordered packing. If I assume a random packing, it's going to be 0.64, okay, and if I have a way of calculating Fractal dimension, there will be some way of kind of, writing this, the structure of the aggregate in terms of the packing fraction, right, and rho p is the density of the particle. If you know the parent particle that you are going to use, right, I know the rho p, I know the properties of the fluid in which the particle is settling, right. The only thing that I don't know is what is d aggregate, okay, that is the dimension of the aggregate. If you have a way of measuring the aggregate dimension, okay, there are ways by which you can measure that, okay. If I have aggregates in a solution, okay, whatever method that people use for particle size measurement, people can use a similar methods for measuring what is the d aggregate. Therefore, if I have a way of calculating this or measuring this, I can actually substitute this back into this equation, and I can actually calculate what is the ut aggregation, the terminal velocity of the aggregate that is settling in a fluid, right. What you can also do is I can actually do further simplification and then try and express this ut aggregate in terms of the settling velocity of the particle itself, okay, and the way to do that would be yeah. Yeah. No, I'm so see what I'm trying to say is that, look, if I assume that it's an impermeable aggregate, okay, it has some characteristic size, it has some characteristic density, okay, I'm assuming it as a spherical aggregate, and that is settling in a fluid, okay. In such case, I mean, this is going to work, right, because the projected area is still, I'm going to assume it as a 4 pi r square. Again, as I said, right, this is a simplification, okay. The reason why it's a simplification is because if I take aggregates like this, is more complicated, right. You should, for example, the case 1, I have to worry about whether this linear aggregate that you have at what orientation is settling. That becomes important, right. Okay, so we have kind of simplified this problem, and all that I am saying is that if you assume the aggregates to be spherical, okay, if I am assume them to be impermeable, okay, the effective your AP, which is the projected area, is still going to be pi r square, okay, which is the pi times the radius of the aggregate square. That's all, right? Okay. So yeah, so maybe I'll stop here. So we kind of set up the problem now, okay. So we have a way of thinking about, if I assume that the particles are settling or the aggregates are settling in Stokes regime, I can, whatever formalism that we did for settling of solid particles, I can kind of rework that and then use a similar kind of formulation also for aggregates. We'll try and continue with the rest of the class tomorrow. Yeah, thanks.